So the next demo is application-aware G-SRv6 network-enabled 5G service. The demo will be given by Cheng and Jianwei. Cheng is graduated from BUPT and worked for Huawei as an IP standard representative in IETF, focusing on G-SRv6, SRv6, SFC, etc. And Jianwei Mao is graduated from BUPT and worked for Huawei as an IP research engineer, focusing on G-SRv6, SRv6, APN6, CFN, etc. Okay, thank you very much for presenting the demo. You're on.
Hello guys, I'm Cheng. I come from Huawei. Can you hear me?
Hello everyone, my name is Jianwei Mao and I come from Huawei. I'm glad to introduce our demo paper for you. It is application-aware G-SRv6 network, enabling 5G services. Let's talk about why we need to propose this project first. As 5G and industry verticals evolve, ever-emerging new services are accessing to the network, and they have diverse but demanding requirements such as low latency and high reliability. Different applications have differentiated network service level agreement. For instance, online gaming has highly demanding requirements on latency. Live video streaming has high requirements on both latency and bandwidth, while backup traffic mainly requires more bandwidth but is less sensitive of latency. However, in current networks, the operators remain unaware of the traffic type traversing their network, making the network infrastructure essentially dumb pipes and losing opportunities to optimize application performance. In order to enable networks to be aware of applications, we have proposed APN6 solution at INFOCOM 2020 workshops. By conveying application characteristics information in the data packet and into the network, APN6 makes the network aware of applications requirements in order to guarantee their SLA. Next, SRv6 is the latest underlying network protocol and supports APN6. SRv6 enables the ingress node to explicitly program the forwarding paths of packets by encapsulating or inserting ordered segment ID list, the seed list, into the segment routing header at the ingress node. And each seed is 128-bit long. The SLA of applications can be satisfied by steering the application packets into an explicit SRv6 programmable forwarding path. So 5G services will benefit from SRv6. However, in some scenarios, such as strict traffic engineering, many seeds will have to be inserted in the SRH, resulting in a lengthy SRH, which imposes big challenges on the hardware processing and affect the transmission efficiency for 5G services, especially for the small size packets in 5G MMTC or URLLC scenarios. For instance, the size of an SRv6 encapsulation with 10 seeds is 208 bytes, which exceeds the parser window of most merchant silicon chipset and causes expensive packet recirculation. On the other hand, it results in a significant increase in packet size for MMTC or URLLC scenarios. In conclusion, the transmission overhead of SRv6 is too high. So we propose this solution to address the challenges of SRv6 overhead. G-SRv6, generalized segment routing over IPv6 network. As we know, within an SRv6 domain, SRv6 seeds are allocated from one address block. So the seeds share the common prefix of the address block. In most cases, only node ID and function ID are different among the seeds in a seed list, while the common prefix and argument parts are same and redundant among the seeds. So G-SRv6 extract the same parts from seeds, moving them to the destination address field of IPv6 header, and finally remain only the different parts in the seed list. The different part, we call it compressed seed or generalized seed. As for network planning, 32-bit is the ideal length for the compressed seed. So one 128-bit space can contain 4 compressed seeds. G-SRv6 only carries the compressed seed in the SRh, so that the size of the SRh is compressed and the overhead of SRh is reduced. In addition, G-SRv6 provides a mechanism to encode generalized seed in the generalized SRh, where a generalized seed can be a 128-bit SRv6 seed and 32-bit compressed seed or some other types. Theoretically, using G-SRv6, up to 75% overhead of the SRv6 seed list can be reduced. In another side, G-SRv6 can reduce the locators of SRv6. That means if you want to deploy G-SRv6, you don't need to apply for new IPv6 address blocks, and you don't need to advertise new IPv6 routes into your network. So you can deploy G-SRv6 incrementally and on your demand. It is fully compatible with SRv6. Okay, based on G-SRv6 and APN6, we propose application-aware G-SRv6 networking. We achieved application-aware control, which is based on SLA requirements of applications. And you can steer different application flows to suitable TE tunnels by programming your network the same as you do with SRv6 before. But please notice that now you are using more efficient encapsulation, which is provided by G-SRv6. We implement a demo for this based on Linux kernel and Huawei router. In detail, for APN6, we developed some functions to encapsulate APN6 options with application-specific information in IPv6 hop-by-hop options header. For G-SRv6, we built a kernel module to identify APN6 information and select the most suitable G-SRv6 TE tunnel for specific application flows. And it can encapsulate G-SRv6 routing header to packets. Besides, it's supposed to perform COC flavor for AND and X behavior and do some necessary behavior of SRv6 and maintain a G-SRv6 local seed table. And we set up a 3-layer topology for this demo and program 3 TE paths with different characters. All of the paths are with about 10 hops. That means there are about 10 seeds in the seed list. As for 3 main scenarios of 5G, we use 3 applications and test their performance in SRv6 and G-SRv6 solution. because APN ID represents the type of 5G services or which application the traffic belongs to. We can steer the traffics of the 3 applications into suitable TE paths according to the APN ID. For the result of performance test, we can see first, forwarding rate of G-SRv6 is 55% higher than SRv6. In further test, it grows from 400 millions of packets per second to 620 millions of packets per second. Second, for the MMTC and URLLC scenario, which packets contain only about 128 bytes in the payload, the transmission overhead is reduced by 50%. In addition, we can see the bandwidth utilization is improved by about 10%, and the flow completion time is shortened by 10%. Okay, here are my teammates. If you have interest for our project, please send us an email. Here are some document and video materials for your reference, and you are welcome to join our open communities. Thank you for your listening, and thanks for my teammates. Thank you.
Sorry, I was muted. So Jianwei is here and Cheng is here. So are there any questions from audience to these authors?
Yeah, if you have any questions, come up and go ahead. Thank you.
So let me lead the questions here. So very interesting work. So I think definitely the demonstration shows the effectiveness of your method. Compressing the SID and show the much lower payload here. I just have a question whether this compressed SID could applicable to any type of applications, or is there any limitation? For example, some application may not support this.
Well, this method is working for IP layer, so we don't really care about what kind of applications be carried within the payload. So everything is supported. Yep.
Okay, I see. So you also mentioned that you utilize this compressed SID to as a control network layer to support your application aware method. So in this application aware method, did you try what kind of application you tried? I saw you have tried the stream video, right? And it seems to me that most applications that you tried are video playback. Are there any other types of applications you use in the evaluation?
Hello. In our evaluation, we use the file downloading.
Okay.
This is the first application. And the second is the high definition video on demand, or the live stream. And the third one is the interactive control. That is the same as the MMTC or URLLC scenarios.
Okay. So when you say that you have application aware, do you consider other any applications other than that? I saw in the motivation that you also mentioned that because the 5G also trying to support those low latency application like video games or VR user interactions. Are they so video games usually
Yes.
And VR usually not just involving the video, right? And also integrated with other type of data.
Yeah, we plan to support all of the applications in the future, and right now it is a simple demo of showing how to support 3 typical services. Yep, but in future we will try to implement this on like Huawei devices to support all the applications. Yep.
I see. Thank you very much. Yeah. So
Thank you.
Yeah, thank you.
any other questions?